The basic task of the independent samples t-test was to compare two means. So you have mean from population 1, mean from population 2. You go out and sample the populations. You do your study, collect your data. Then you compare the two means and make an inference to the difference between the means occur by chance or not. So the t-test is based upon the simple comparison of just two means. Now, what if you want to compare more than two means at one time? Well, the analysis of variance is what's going to let you do that. And just imagine you have a display like this in which you've got another curve, in which you've got another population, and you want to compare three means, or more than three means. Imagine you've got 20 groups. You want to compare the different ones. Well, analysis of variance is the general procedure for analyzing sets like that, and we're going to go over that in this introduction. In this introduction, we're just going to go over the basics of what analysis of variance is, and basically how it's applied. We'll do some examples in SPSS, some very simple, straightforward examples. Well, analysis of variance is a way of typifying the ratio of variability across the means, across the groups, versus the variability that's within each sample. And we'll get to that, what that means specifically in a second. It was invented as an extension, really, of the t-test, because a guy named Fisher, who invented the procedure, he was given a lot of data to analyze. He didn't want to do a t-test for every pair of groups. He wanted to develop something in which he could compare across groups in a very efficient way, and if there was a difference for at least one of the means in his analysis, then he could follow that up with pairings to see if there was a specific difference he could find. So it was kind of a practical problem he had, and it had to analyze lots of different means to find out if they occurred by chance or not. He didn't want to do them one pair at a time. You also have to imagine back in those days, which must have been in the early 20th century, Fisher did not have computers to do his analyses. So any analyses he had to do had to be done by hand. And you could imagine doing t-tests by hand, one after the other, would take a long time to do. And it's also subject to a lot of errors if you make that many calculations. Now we can do all the t-tests we want anytime we want. We can compare every pair of things in 10 or 20 milliseconds. The computer calculates everything. But back in his day, he had to be efficient, and so he developed the procedures of analysis of variance to handle this. Fisher apparently was a very irascible person who was very hard to get along with, and it was very hard for other statisticians to learn what he was doing. He was kind of idiosyncratic. They could tell that he discovered something pretty significant, pretty important in analysis, but they could never quite get all the answers out of him. And eventually, of course, he published everything, and people figured out what he was doing. He was analyzing data from agricultural studies, and so analysis of variance actually emerged from studies of crops being grown in different conditions. And there were so many different conditions they had in the data set that Fisher decided, well, I've got to figure out a way to compare lots of means at one time. If there's one of them that's significant from at least one of the others, then I can follow it up with an analysis. If none of them are different, then there's no point in following it up with every contrasted t-test. And so this way he could do lots of analyses at once. If they were not significant, then he didn't have to follow them up with more and more analyses. You also have to imagine that he's working mostly in an area, what we would kind of call quality control, or in an area where we don't want to see differences. When Gossett is making beer in the Guinness brewery, they don't want to see differences across the batches of beer. Differences in the batches of beer means that somebody made one batch, very different than another one. And they want all the beer to be very consistent. They want it to be the same. So they want every batch to have the same mean value for alcohol level, the same mean value for sugar level, the same mean value for whatever else they measure. They don't want to see differences. So Fisher's in that kind of environment where not seeing differences is preferred. Now in psychology studies, theories that specify a difference. And we're not in quality control. So we want to find differences if they're there. And a lot of times our theories are proposing significant differences. All right, well, at any rate, here's some examples of different settings in which you might use analysis of variance. Here's a very simple one where you're comparing freshmen, sophomores, juniors, and seniors. That's 4 groups. You're going to have 4 means. Now, if you wanted to study this with t-tests, You'd have to compare the freshmen to the sophomores, the juniors, the freshmen to the seniors, and the sophomores to the juniors, the sophomores to the seniors, and so on. You get all these combinations of t-tests you'd have to do. You may have to end up doing that anyway, but the analysis of variance will tell you if any of these means are going to be significantly different from any other mean. And if they aren't, then you don't need to follow it up with a t-test or other kind of post hoc test. Here's some others. Reaction times for baseball players versus basketball players versus players. And in general, the analysis of variance answers the question of whether two or more groups are reliably different from each other. It's the same logic as the t-test, it's just now it's being applied to more than two means. The logic of the analysis of variance is the same basic logic as the t-test. The null hypothesis is slightly different. The null hypothesis of ANOVA is that several populations being compared all have the same mean. Testing the hypothesis involves an analysis of the variance of the study samples, and this concept of variance is not any different than the concept of variance that we've learned up so far. It's just that we've not really contrasted it as variance. We haven't contrasted sources of variability, generated a ratio from that, and done our inference. We tend to compare means directly and then compare that mean difference to variances in the samples. Now, when we compared the mean difference in t-test, that mean difference was actually a measure of variability, if you think about it. Variability, again, is the distances of a score to a sample mean. Any kind of distance measure, any kind of measure of one score away from another score is a measure of variance. A mean difference, two means different, that's a distance measurement, distance from one mean to the next mean. Now imagine you've got more than just two means. Now you've got something you can actually average across a number of means, these distances, to get an estimate of how far apart the means are as a group. And we'll get to that in a little more detail in a second, but basically we're going to treat that as a source of variance, compare that to the same kind of variance that we calculated before for the t-test, and then make an inference about the mean differences. Well, how do we estimate variance in analysis of variance, or in t-tests, the same kind of contrasting? Well, first of all, we don't know the variances of the populations under study, and we're going to need to go sample them. So we don't know what the variance is, just like we didn't know in t-tests. And we're going to go sample the populations and estimate from samples. Well, there are two estimates of variance that are classic in analysis of variance, and you got to sort of get this burned into your head. There's two ways to estimate variability. One is the variability within each group. So imagine you've got three groups, and you're going to have variability within each group. So the individual subjects are going to be varying around the mean of the group they're in, the sample they're from. And then you're going to have estimates of the differences between the groups. So you're going to have a variance estimate of how far the means of each sample are from each other, or the means from each group are from each other. You see, now you've got more than two means. So now you might have, 3 means or 10 means, but you've got a set of means now. They're all going to be different distances from each other, and you're going to calibrate that as a measure of the variability that's in the study. So you have two sources of variability, one that comes from the differences between groups, and one comes from the variability that's within the groups. Now we pool the estimate of the variability within groups into one score, into one value. And it's the average amount at which the subjects within the samples are varying from their means. And it's called the within groups estimate of the population variance. So now it's going to be estimated, since it's estimated from samples, it's going to be an estimate of the population variance within groups, not across groups, but within groups. All right, the between groups estimate of variance refers to the differences between the means. So each sample has a mean. Imagine you've got 3 means then, because you've got 3 groups. There's going to be variation among these. One mean is going to be slightly closer to the next mean in a dependent measure. And you'll have variability. So the means will be far apart from each other. They'll be close to each other. They will vary. And this variance has to be calibrated. as a measure of how far apart they are. And this variation represents an estimate of the population variances. So if you have situation 1 here, when the null hypothesis is true, and when all the population means and variances are the same, so that's when the null hypothesis will be true. So all the population means will be the same. There won't be variability among them. All the variability will be in the study will be captured by the variability that's within each sample. Now, when the null hypothesis is false, so there is a difference between the means, then some of the means will be far apart, or at least 2 of the means will be far apart from each other, and they'll be significantly different. It couldn't have occurred by chance. So in that situation, a lot of the variability that's within the study is going to be captured by the variability across the means of each sample, as well as the variability that's within each sample. But now the distances that the populations are apart from each other, captured by the distances that the means are far apart from each other. Now, if all the means are the same, when the null hypothesis is true, that doesn't prevail, and all the variability in the study is captured by the variability within the samples. But if the null hypothesis is false, if there are differences between the means, then part of the variability in the study comes from the distances across the groups, and not just within the groups. And we'll contrast these 2 sources of variance in a ratio that allows us to make an inference about whether the means of the groups are significantly different or significantly far from each other. Let's take a look at this graphic that depicts that situation. We're still kind of focusing on the between groups estimate of variance because that's a sort of a new concept. Even though we've actually used it before, we didn't really call it that. We just call it the mean difference. But now that we've got more than one mean, it's now going to be a source of estimating variance that's in the study. Okay, well, situation 1 you see here on the left. In situation 1, you've got 3 groups, and the population means of these 3 groups are the same. And when they're the same, the means are similar. There's less variation across the populations. You can see if you take the means and drop them down to the bar at the bottom, you see that there's less variability. They're closer together. The null hypothesis is true. The population means are the same. And so you see where there's less variability when you drop the means of samples, and showing little samples here. If you take samples and drop the mean down there, where there's less variability in the study, you see that they're close together. If you go to the right one here, you see the same situation where the means are the same, but there's more variability within each population. See how much broader those are than the ones on the left? Now when you take samples out of those distributions, you get this variability at the bottom. See how there's variability now across those 2. They're further apart. The means of those samples are going to be further apart because the mean within each population is greater. So if you look at this, you can see that the between groups variability, the distances between the means at the bottom here, is going to be an index of how much variability is within the study. And that's when the null hypothesis is true. So the between groups estimate becomes an estimate of variability within the study. If you have a lot of variability in the populations, you're going to have more the mean differences will be greater. You can see how that would prevail here if you chose means at random. Now let's take the situation where the null hypothesis is false, and we have different population means. So now we've got a set of means. Now all these, you notice that all the variances within each one of these samples, within each one of these populations is the same. And you see on the left there, if you take samples out of those populations and drop them down to the bar below, you get an estimate of the variability that's within those populations. Now, however, if you go to the right and look at the situation where you've got one mean that's standing out, so one mean is very clearly different than the others. When you drop that sample mean down at the bottom bar, you get a big gap there. And that big gap is reflecting the variability that's across between the groups. And it's telling you that there's probably a mean that's different. So if you were to calculate the variability on the right side, it's going to be much greater than the variability on the left side. And that's what happens when there's a mean that's different and the null hypothesis is false. So now we've got an estimate of variability in the samples within the study that's much greater, and it's being reflected by a difference between the means. Now let's compare the between groups estimate to the within groups estimate of variance. When the null hypothesis is true, so none of the means are different, both estimates should be about the same. So samples are being taken from distributions having the same mean, they all have the same variability. The estimate based upon the between groups estimate and the estimate based upon within should be about the same. So the ratio between them will be 1.0. However, when the null hypothesis is false, when you've got a difference between the groups, now you've got a different situation. The between groups estimate of variance will be influenced by both the variations within each population and the variation of the means of the populations from each other. In that situation, when the null hypothesis is false, when there are mean differences, the between groups estimate will be larger than the within groups estimate of variance. Okay, so when the null hypothesis is true, the ratio of the between to within groups estimates of variance should be about 1.0. They should be about the same. When the research hypothesis is true, the ratio should be greater than 1. Okay, so the ratio between to within should now be greater than 1 because now the between groups estimate is being influenced by the differences between the means. And that ratio is going to be a nice reflection of how generally the means are different from each other relative to the variability that's within each sample. Now remember with the t-test, we did that with two means. We subtracted one mean from the other, and we made a ratio of that subtraction to the within groups, variability, the pooled variance of pooled variance estimate. We were doing the same thing, which is called something different back then. Now we're going to call the mean difference the between groups estimate of variance, and we're going to contrast that with the variability that's within each group. Now we have the two parts to calculate Fisher's F ratio. Okay, an F ratio is the estimate of variance between groups divided by the estimate of variance within groups. Okay, it's that contrast that we just described in the previous slide. If the groups are different from each other, then the variance estimate between should be greater than the variance estimate within, and so F should be greater than 1. If the groups are the same, then the between to within variance estimate should be the same, and so that makes the F ratio approximately equal to 1. Now we get to the issue of making the inference and statistical significance. So now we have this ratio between to within of variance estimates. If the between is large, it means that the means are different. If the between is large, it also means the F ratio is going to deviate, become larger and larger than 1. Well, here's the question. How much greater than 1 must the F ratio be in order to be considered significant? Well, you have to generate another distribution of probability. And here you see a nice classic probability density curve. This is similar to the curve we saw with the t-test. It was the probability for different t's, and now you're going to have probabilities for different F ratios. So F ratios, you can see 0 is obviously going to be very small. There's a 1 there, 2, and so on. And you see where as it goes above 1, the probability becomes less and less. Now what was calculated is a set of cutoffs for probability levels that correspond to the conventions we've used before, like 0.05 and 0.01. And then these were published in tables, just like the t ratio, just like the t distribution. Now we have an F distribution. These cutoffs were published because obviously if you published every single probability value for every single F score, it would just be books and books of tables. Now SPSS will actually calculate the probability directly. It takes this curve here, and what you're going to be doing for probability, see, is estimating the area under the curve. If you know a little calculus, you can figure that out. SPSS does that directly. It gives you a probability of a certain value associated with a certain F ratio, If you use the tables like in your textbook, though, you're going to be looking up the F ratios that correspond to different probability levels. As you might imagine, these F tables are going to be calibrated by the sample size and the degrees of freedom, because the larger the sample size, the better you can represent the relationship of the between to within, and so your F values can be smaller if the sample sizes are larger, in the sense that a smaller one might be discovered to be significant. As your sample sizes get larger, the F ratio becomes less stable, and so the estimate of probability is going to change and be calibrated by that. That's what tables in the book will show, is different cutoffs for, say, the 0.05 probability level for different sample sizes. Remember, sample size is also converted to this concept of degrees of freedom. They're the same concept, except that degrees of freedom has to do with constraining essentially the number of intervals between numbers rather than the total sample size itself. It's always n minus 1 for degrees of freedom versus n, just the number in the sample. Okay, how do we calculate these variance estimates? Well, the within group's estimate of variance is going to be the distances of individual scores to the sample means. You see that represented here in an equation. X is the score minus the mean squared. We're going to take the sum of those. So that's going to be the sum of squares within. Now remember, you square everything just to get rid of the negative sign. So the distance is going to be calibrated that way. It's the score minus the mean squared, and then you're going to add all those up, and that's the sum of squares within. Now we're going to do something a little bit differently with the sum of squares between. Notice there's a term in there called GM. GM refers to the grand mean. Now the grand mean is the average of all the subjects in the study. Okay, so it's the big mean. It's the average of everybody's score in the study. And what you're going to do is subtract the mean of a sample from the grand mean and square that. Say you've got 3 groups. They each have a mean. That's M. Subtract the grand mean from that number and square it. Then add those together. And that's the sum of squares between. Now we're going to be doing an example with Excel. Spreadsheet, Microsoft Excel, a spreadsheet program, and we'll be also doing some SPSS examples in which this will be clarified. So just keep in your head now the grand mean. What that means is the mean of everybody in the study, and you're going to be subtracting the means from the samples from that grand mean to get essentially what this is. It's a general index that measures how far apart the means are by using a common reference called the grand mean. Okay, finally what you do is you divide the sum of squares within and the sum of squares between by their respective degrees of freedom. And we'll talk about how to calculate each one of those in a second. But now that's going to give you the variance within, and the variance between is going to be the sum of squares between and the sum of squares within divided by their respective degrees of freedom. And these degrees of freedom are different for each one of them. It's not any radically new idea. Just keep it in your head if they're different degrees of freedom numbers. Okay, here's an example that might help us get us focused to understand what between and within estimates of variance are. Here you have an example where a personality psychologist wants to know whether birth order, whether you're firstborn, secondborn, and so on, is associated with your leading ability, your ability to lead other people. So the psychologist tests the leadership abilities of 5 firstborns, 4 secondborns, and 4 thirdborns. At the probability level of 0.05 at 5%, what should the psychologist conclude? The psychologist goes out and collects samples of firstborn children, secondborn children, thirdborn, or adults, I guess. I guess it doesn't really matter. And tries to find out if there's a relationship between this category of being of birth order and the dependent measure of leadership skill. So here's the setup for the problem, and now we'll go through it. Okay, well, step 1, just like before, is we have to restate the research question, refer to hypotheses and populations, and restate the research question as hypotheses. Okay, so the research question is, Is leadership different for firstborns versus secondborns versus thirdborns? The research hypothesis is that the population means are different. And notice here it's not necessarily that they're all different from each other, but at least one of them is going to be different from one other one. The null hypothesis is the population means are the same. Okay, the next step is to determine the comparison distribution. Now, as you might imagine, after all this preamble, our comparison distribution is going to be an F distribution with our degrees of freedom equal to 2, because we have 3 groups. So degrees of freedom are going to be the number of groups minus 1. And the degrees of freedom within are going to be the sum of the degrees of freedom for each group. And we'll calculate that in a second with a spreadsheet. But basically it's going to be the degrees of freedom for each group. It's going to be size minus 1 for each group, and then those added together. Okay, the next thing we got to figure out is the cutoff score for our 0.05 significance level. And you go back to the F table in your textbook. If you have degrees of freedom of 2 and 10 with 0.05 significance, you'll discover that you need an F score, an F ratio of 4.26 to conclude that a mean difference did not occur by chance. Okay, so you're going to figure out F ratio, and then you're going to compare that F ratio to this cutoff score for 0.05. If it's this score or higher, then it's unlikely that the mean difference that you found occurred by chance. Okay, now we're going to do something like we've done before, where we've gone to the course website and downloaded a data file or something like that. We're going to download a spreadsheet which has all this firstborn calculations in it. So go to the course web page and download a spreadsheet called Firstborn Excel Spreadsheet. Now you need to have Microsoft Excel installed on your computer. Chances are you have it because you have Microsoft Office. Otherwise you have to get it, and there are various ways of getting it, but basically you probably have it. Okay, you want to open the spreadsheet with Excel. So double click on the file icon or run Excel and then open the file from there. And you should try to have this presentation up along with the Excel spreadsheet so you can go back and forth between them as we go over the calculations. It'd be nice to be able to change numbers and, see what happens and stuff like that. So you've got this window up with the presentation and a window up with the Excel spreadsheet. Your Excel spreadsheet should look something like this when you open it up. If it doesn't, then you've got some kind of a problem and you need to go investigate why Excel is not running on your computer or some trouble in downloading the file. But if you run the spreadsheet Excel and open the spreadsheet, you should see it look like this. And these are all the calculations for the analysis of variance for this example with the birth order. The first thing I'd like you to do is to examine the Excel spreadsheet by clicking on the cells in the spreadsheet to see how things are calculated. You may not quite understand exactly what's being referred to. I think you can figure out, even if you don't basically know anything about Excel, how it's referring to cells by their row and column designations. And you can see where, okay, if this 5 here is being summed with this 6 over here, and figure out how the calculations are made. If you know something about Excel, you can see that they're basically, this is a very simple spreadsheet in Excel. It's either just a simple number being entered, or it's a reference to a cell somewhere else. And so a few places you'll discover there's actually been some variables specified in Excel, like the means and so on, because there's something that's referred to by a number of different cells. Okay, next I want you to look at the means for each group. So look at the means under each birth order, and there's 1, 2, and 3 there. Look at where those means are, see how the scores are being summed and averaged to produce the mean. So there's a term called the grand mean. And this is the average of all the scores in all the groups. You can see it's referred to as GM. Notice how you calculate the variance, the degrees of freedom, the sum of squares between, and the sum of squares within. So click on those cells, see what cells they're referring to, and you can see where it's picking up the sum of squares like we did before. In regard to this, you notice a little caret on number 2. This refers to squaring. Remember, we're going to square the scores to the mean. We need to square those and add them together. And that's how you indicate squaring in Excel with that little caret, that little character that's above the 6 on the keyboard, and the number 2. Notice the computed F ratio. Notice when you click on the F ratio how it's brought together those cells that refer to the ratio between to within sum of squares. And finally, what I'd like you to do is change some values in the study to see how that affects the calculations. So don't add subjects, substitute values that are there already, make them real high or real low so you can see how it dramatically affects the F ratio. And if you increase the variability within the samples, you'll see that the F ratio goes down. If you increase the variability across the three groups such that their means are different, you'll see the F ratio goes up. So just play with that, just interact with it, and see what kind of values are calculated when you change the numbers. I think that's one of the best ways to see how these values are calculated, by changing them to see what happens to the numbers when you do that. And notice also that the grand mean changes every time you change a value. So the grand mean is going to be adjusted depending upon what the sample scores are, what the individual scores are. Now we're going to do the same analysis with SPSS. This is the same analysis that we just did with the spreadsheet. So you need to go to the course webpage and download the data file for SPSS. Open an SPSS. It should be called something like birth order data, birth order SPSS file, something like that. And once you get SPSS open and everything, you should have this presentation open along with SPSS. Go to the Analyze menu in SPSS, choose Compare Means, and then choose One-Way ANOVA. Indicate that leader is a dependent variable and birth is the factor, which is SPSS's way of calling the grouping variable. Click the Options button. Choose Descriptives, because we want to be able to see the means and the variances and so on. If you don't choose Descriptives, it just gives you the F ratio. Click Continue, and then click OK. And then on the next slide, we should be able to see the output. But I want you to try to SPSS. Don't just look at the output only on the slide here, to try to figure out if you can do it. If you run into trouble, check the textbook when it explains how to run SPSS. If you notice that it's not loading in the data file, you don't have these variables called leader and birth, then you need to track that down and figure out why the data is not being read. You should have SPSS output that looks something like this. Now obviously this one's going to be hard to read because the SPSS itself doesn't produce a font size that's very large. But you should be able to read the one that's in the SPSS program, so you should be able to look at this table in SPSS. What I want you to do is look over the calculations and compare them to the spreadsheet. So look at the means. You can see the means there are the same. The sample sizes of 5, 4, and 4. The mean is 7, 6, and 3.7. And the standard deviation, and so on. And then the lower table gives you the ANOVA results. It gives you the ANOVA table. You can see they're between groups. Sum of squares is 24.019. Within groups, sum of squares is 34.75. You see the degrees of freedom of 2 and 10. You see the mean squares, which is the sum of squares divided by the degrees of freedom. And then finally you see the F ratio, which is the ratio there of between groups variance to within groups variance. And you get 12 to 3.475. That indicates an F of 3.456 and a significance level there of 0.072. Now 0.072 does not meet our cutoff. It's close to our cutoff of 0.05, and our cutoff here, or our significance level here, is 0.072. Now notice that SPSS gives you the actual probability. It does not do a cutoff thing. It doesn't have to do that. It can actually calculate the probability value for a certain F ratio. If that probability value is smaller than or equal to the cutoff you've chosen, then you can make the inference that there's a mean difference here that did not occur by chance. It probably occurred by design. You may notice that some of the numbers are slightly different than the ones in the spreadsheet. This is because Excel, depending on how you set up Excel, it uses precision of probably just 2 decimal points, whereas SPSS probably uses a precision that's much more accurate. So you should see small variations in the numbers, but they should be basically the same. Okay, the assumptions of ANOVA are the same as the assumptions for the t-test. The populations have to follow a normal curve, and so there has to be this bilateral curve, this symmetrical curve like you see called the bell curve. And the populations have to have equal variances. Now, obviously, we're doing variance estimates. So if the populations have unequal variances, then we've got a problem. Then we can't use the F ratio calculations the same that we have. See, all the probability judgments are based upon the idea that you've got variables with a standardized looking normal curve. There's nothing, skewed about the distribution. There's not a distribution populations. One isn't extremely narrow and the other is quite broad. If these are all going to be relatively equal. Otherwise, the probability judgments will be off. You've got to then make separate tables for the odd situation that you have. Generally, if researchers are doing a study in which there's big differences in variance, skewness, they transition to other kinds of statistical procedures. Now, it has been shown that you can you can violate these assumptions to a great degree, and still maintain your inference. You'll still be pretty much on the money, but of course, there's always a point at which you violated the assumptions too far, and you have to transition to a statistical procedure that doesn't require that you have a bell curve and that the population variances are equal. You have a unique problem with analysis of variance that you don't have with t-tests. In analysis of variance, when you get a significant F ratio, it only indicates that one mean is significantly different from at least one other mean, but it doesn't tell you which mean is different. Here you've got 6 means. They're all the same except for one. Well, if 2 or 3 of them differed from the others, would result in the same significant F ratio. And we wouldn't know which means were different. So we have to do some kind of a planned comparison after the F ratio is calculated if it's significant. Now see, Fisher and them, when they're doing their original F ratios, they didn't particularly want there to be a difference. But when they found one, they had to go back and pursue, okay, which one is different, and then investigate why. So we have to do the same thing. Now, the most common procedure that's done is to do F ratios for pairs of means, or to do t-tests. And they're very they're essentially the same procedure. It's just that you're going to be now doing every possible pair to find out which one is different. Finally, we have another problem with analysis of variance. It's the same kind of problem we have with the t-test. It's the same basic issue. If you do multiple planned comparisons with ANOVA, that means you're going to be doing a lot of t-tests or f-tests for every pair of means. We started that originally with t-tests. Suppose you had 20 pairs of means. You could have done 20 t-tests. Here you may end up doing the same thing if your F ratio is significant. Well, now we've got a p-level of 0.05 of 5%. Well, imagine if you flip a coin one time, the chances of heads is 0.5. If you flip a coin 10 times, the chance that it will turn up heads one time out of 10 is greater than 50%. So if you do a set of t-tests or f-tests, if you perform 10 planned comparisons at the 0.05 level, the chance that one will come out significant is greater than 0.05. So imagine if you did 50 t-tests. Well, 5% will come out significant just by chance. Remember, we've got this chance level going here of 5%. So 5 of them will be just by chance. We may have to interpret, that they're meaningful. That causes a problem. Well, the correction for this is to use something called the Bonferroni correction, and that's where you divide the p-level, the probability value, by the number of comparisons. So instead of having a 0.05 level of significance, you divide that by the number of comparisons to get a much more conservative number. The problem with this approach is it can become way too conservative. You may end up attributing to chance things that actually occurred by design. I don't think the field has resolved this issue. The Bonferroni correction is far too conservative. It does correct for this, but you'll end up doing an entire study and discovering that nothing's significant because you've Bonferroni corrected your p-value to be so small that only very, very large differences come out significant. Probably the way to deal with this, I think, is to look at the theory of what you're studying and to identify certain comparisons and certain mean differences that have to be there as a test for your theory. If you're just going out there and collecting lots and lots of data on lots of subjects, say you collect 100 dependent measures on 1,000 subjects, just to see if something's going to come up significant, then this p-value issue will work against you, and you'll end up with significant findings that are absolutely meaningless. They just occurred by chance. But if you go out there and say, okay, I have this theory that this drug that I've made here should cause a certain effect size for this kind of infection, and you've got a good measure of the infection and what it does, and you go out there and you measure that, and even if you measure 50 other things along with it, that one hypothesis, that theory that you said, this drug should work this way, of this magnitude, should get you to focus on that one statistical test as if it was the only one you're doing. And if it doesn't come out significant, then it's unlikely that your theory is correct. That's how I would handle this. I think the field generally, is going to bend this way, because doing it this way produces such a conservative posture that it's more conservative than we need to be. And maybe some correction values or some correction system will come up that's not so. I have a feeling, though, it's not going to help as much. If you just look at statistics in a blind way without any kind of theory guiding you, these kinds of things are going to happen no matter what you do. And the way to solve this is to focus on fewer variables, so you have fewer dependent measures, so that fewer of them will occur by chance, and making sure the dependent measures that you measure are strongly related to a theory of why you're doing the research to begin with.